So let's try a problem out here real quick. IQ scores. I think they use that in the homework. They're normally distributed. The mean is 100, and the standard deviation is 15. So it's probably somebody has more than 140 IQ. A few of you guys lost points because you didn't draw the picture, so when you looked up the z-score, you thought you were done. When actually the question wanted the area above and wanted the area on the other side, and if you just would have drawn the picture, you would have known that. You would have finished it out correctly. So what goes right in the middle? 100. So 140 is definitely over here. A few of you guys were putting like 7 here and then 2 there. That's disturbing. It's definitely just a real number line, right? So the numbers have to go bigger numbers over there, smaller numbers over there. And then what area do I want? Yeah. Above 140. I want that area there. So right there, I know I expect it to be less than 50%. At least I can say that. Right? So if I get an answer of 80%, something's very wrong. So what's the next step here? Beautiful. So here's something I didn't really show you guys before, but normally a classic z-score problem, they give me an x-score, like an IQ score or a shoe size or whatever. There's the one they give me. I change it into a z-score, and then I look that up to get the percentage, right? So this is using formula, and this is using chart. Cool? The funny thing is you can go exactly backwards. If they give you a percentage, like they say find the IQ that would put somebody in the 80th percentile. They gave you a percentage. You look up the z-score using a chart, and you change it to a raw score using a formula. Right? It goes both ways. XZ's percentage, percentage Z X. That's your standard classic z-score problem. You have to be able to do this kind of problem relatively easily so you can handle like the central limit theorem stuff. When I say I take 80 people, what's probably their average IQ is this. Then you have to make a tweak to this stuff, right? You have to change the standard deviation. What would the z-score formula look like here?
140 minus 100.
Beautiful. My data point that I'm interested in, minus the mean.
Or 15.
Divided by 15, I love it. What do you get there?
2.67.
2.67 sounds about right. You got like 2.6 forever.
Mm-hmm.
So what do you get when you look that up? 2.67. What do you get when you look that z-score up?
0.9962.
All right. So see, this is a really heavy suggestion, right? You don't have to do this because some of you guys are actually doing fine without drawing anything. I love it. That's great. You're showing me enough work and you're not drawing anything, whatever. That's beautiful. But my suggestion is draw it, and the minute you look at that z-score, you put it where the only place it can go is below the one you just looked up. That's the only thing the chart can tell you. So did I find my answer?
No.
No, because I want the area up here. Yeah, so you need to do 1 minus this. Oops. So 0.0038. So there's a question on there, a bonus question that I was hoping some people would try to answer, and if you did, what does that mean in the real world? What's that number I just found, that 0.0038? What's it actually mean in the real world?
Of having an IQ above that.
Okay, right?
Then only 0.38% of the people above your data point.
Exactly. So only 0.38% of the people, I'm assuming this is the United States, only 0.38% of the people in the U.S. have an IQ above 140. Right? So if you have an IQ above 140, you're in a very small group of people. Okay. It actually has nothing to do with how smart you are necessarily. It just has to do with the potential of how smart you can be. So part B here would be part 2. So there's that. Can you find the IQ to put someone in the top 12%. So the first thing is the same as always. Now I draw the picture, but where am I at now in this whole scheme of things? On this one, I was given an IQ score. I had to make it into a Z so I could look up the area. Now they give me the area, top 12%, which I have to do something with maybe. I want to look up the Z score and then make an X score out of it. Right? I want to do everything in reverse. So how does this look when I draw it? Of course, what goes right in the middle?
600.
100. And that's a 0 Z score, right? Where's the top 12% going to be? It's got to be up there, right? Here's the top 12% roughly. There's 12%. I don't know what X score is this, but I can look up the Z score, right?
The only thing with that is that you have one 1190, one that's 1210. They have about the same, so which one do you pick?
On the test, I was letting you pick either one. In reality, when they're exactly perfectly on either side, you take the one in the middle. You actually average the two out. The problem is, are you looking up, what number are you looking up? Is it 0.12?
No, 88.88.
The chart only understands areas that are
Below.
So that's 12% up there. What area is this?
88.
Now some people come at me and they say, well, you just changed the problem. No, I didn't. That Z-score, whatever that Z-score is, it's got 12% above it, so it must have 80% below it. It's still the same Z-score. Just that my stupid little chart only understands areas below, so I got to work with it, right? So when you look up 0.88, you get the same problem. You get 0.879 and 0.881, right? But what are those right in between? What do you get? What is that right in between?
1.175.
So when we look up 0.88, I see 0.879 and 0.881. That'd be 1.17 or 1.18. But what's right in the middle then? 1.175. Cool. On the test, some of you guys might realize that number came up on some of your tests. It should, or maybe should have. Right? But I would have taken 1.17 or 1.18. I would have actually accepted either one of those. But this is what it really should be because it's right in the middle. Right? So where am I at now in this scheme of things? I looked at my percentage and got my Z-score, so now I have to find the X score. Who remembers that little formula that kind of goes backwards?
X equals the mean plus Z.
I love it. X equals mu plus Z sigma.
That's the easy way.
I looked at 1.2 in this area.
Here's 0.88. The closer I get to those two, right? That one is 1.17. That one is 1.18. So right in between the two is 1.175. Just split the difference. So we know the mean is 100 plus 1.175 steps, where every step is 15. So if I start at the mean and I go this many steps up, I'll end up, of course, at the correct data point because that's got 12% above it. That's what we just figured out. I like that idea. And again, I told you when we first started doing standard deviation, I said I'm going to call it a step because it makes sense in very many situations, and it makes a ton of sense there. Start here, take this many steps, I end up in the right place. So then I just got to throw it in the calculator, see what it comes out to be. What do you get?
116.175.
126.
126.
126.
A little too much, I think.
116.
You might have put 1.75. It should be 1.175. Maybe that's, yeah. So 116?
1.175.
I got 117.
117?
625.
625?
Yeah.
All right, cool. So if you have an IQ above about a 118, then you're in the top 12% of IQs. In case you know your IQ score, I don't know. Okay. Maybe. All right. So the last question I want to ask you then. me see, maybe I want to do 2 little questions here. Just to get us into the next section. Between what 2 IQs do I find the middle, what, Jeff? I don't know. Oh, middle 70%. I think that's what we were doing earlier. Does that make sense? I want to find the middle 70%. What 2 IQs tell me if you're between those two, you're in the middle 70% of all IQs. Cool? And every time I think about IQs, I always think about Forrest Gump. And you're here, boy. You got to put this. No. So how do I draw the picture? What would it look like? We actually drew this picture earlier. Yeah, right in the middle. I want the 70% right in the middle. In order to find those z-scores, the chart only understands the area below. And are you cool with the fact that if this was -3, this one would have to be +3, right? So I could find either one, and the other one's going to be the other sign because it's symmetric. It's in the middle, so it's got to be symmetric. So if I knew the area below this dude, I'd find the negative one and just take the negative off for the other guy. How are we doing there? Is that... If I could just find one of them, I automatically have the other one. It's just the symmetric one on the other side, the positive one. So what's area is in there so I can use a chart? That's the one we saw earlier, right? 15%. So we look up 0.15 and get as close as you can. What z-score is that? Yeah. In this case, there is a winner, right? There's one that's closer. -1.04 is the right one. Cool. So what's the one up here?
1.1.
Let me see if you guys can take this next step. The formula I want to use is this one. Would you be cool with this if I do this? Does that make sense? You can see what I'm doing there? Give or take. 100, I want to go up 1.04 and down 1.04. Let me just do it in one thing, right? It's not that big of a, ooh, Jeff, that's amazing. What I really love is when students are looking for the plus-minus key on their calculator. No, there's no plus-minus key, sorry. So let's figure out what this is first. And then we can add it to 100 and subtract it from 100 and get our bounds, right? So 1.04 times 15. Oh yeah, so it'll be 15.6, right? So this piece right here is 15.6. Now you want to add it to 100 and subtract it from 100, right? So you can go up from 100 and down from 100, right? Do the plus or minus piece. And some of you guys remember the quadratic formula had a plus or minus in it. So you had to do the plus and the minus separately. So 100 minus 15.6 is 84.4. And 100 plus 15.6 is 115.6. So the 2 IQs, those 2 IQs, if you're somewhere in there, you're in the middle 70% of all IQs. All right. How are we doing? Does that make sense? I mean, that's not that terrible. Okay, hopefully. Okay. Yes?
When you're getting the z-score, when you're looking at the 0.15, are you getting that from the area part or from the z-score part?
That 0.15, is it a z-score? Is the 0.15, is that a z-score? No, right? It's a what? What is that 0.15? It's a percentage, which is also called an area, which is also called a probability. So it lives in the middle of the chart. So, see if I have one with me now. Just make sure everybody gets that step there. And chapter 7, just while this thing is warming up, chapter 7 is where we start to get really practical and where we start to go, well, in the real world, what do we normally actually know? In the real world, do we normally know this? The population mean? No. In fact, that's the whole reason we take samples, is to try to get a feel for what that is. So chapter 7 tries to take this kind of formula and recast it into, you can't use mu, you have to use x bar. Right? And what has to happen if I start taking samples and talk about the sample means? This has to become the new standard deviation, right? Okay. So this guy's up here. Do it. So just to make sure everybody can do this step here. 0.15, you don't want to do this 0.15 because it's not a z-score, right? I don't know the z-score, so you got to look at 0.15. The closest I can get to it is, of course, way the hell down there. 0.15, it looks like the closest I can get to it is that. Every time I see that number, I think Christopher Columbus, right? 0.1492, that's the closest I can get to 15%, right? So what z-score is that? Negative 1.04. So that's where that came from. That's what I'm trying to tell you, though. It's so evil. They're evil little things. Those look like z-scores. Z-scores look like areas. Shit. And that's why some of you guys, you calculate a z-score, you get 0.78 z-score, you forget to look it up here. You just say 78%, yay. No, you have to look it up. You don't have the percentage yet. You got to look it up. Okay. Leave that dude on in case I want. So here's chapter 7. And I'm actually going to start, I think I told you guys this before. I want to do 7 a little bit out of order. We'll end up doing the whole thing, so don't worry. The reason I want to do a little out of order is because 7.2 is really like brand new. 7.3 is old shit, to tell you honestly. So I want to start with 7.3 and get our foot into it and then go back to 7.2 and see why it makes sense. It's got a very similar format. 7.3 takes this formula here. You can do it, Jeff. The one we just used a minute ago, right? It takes that formula and says, how would it change? And I basically already told you how it would change. How would it change if I don't know the average? And in fact, what I'm really trying to do is I'm trying to say, for example, have any of you guys been to a fair? Have you guys ever been to a fair? I actually, to tell you honestly, I have not been to the fair that happens here. But we used to go to county fairs all the time as a little kid. We lived in Georgia, so county fairs were the thing to do. Or even to like Busch Gardens or somewhere like that, if you guys know what Busch Gardens is or whatever. Have you ever been to somewhere where they have a person like guessing your age or guessing your weight?
Yes.
Do they ever say they're going to guess your age or weight exactly?
Yeah.
No.
They're always going to say, I'm going to guess it within something. So the whole point to what we do in statistics is, okay, I have no idea what the lifetime of a Honda CR-V is. So let me take a sample of them and get an average lifetime. And then I can tell somebody, well, I'm 90% sure that it's going to last from this many months to this many months, or hopefully years to years, right? So that's what I want to say. Or I want to see, what's a good example? What to expect. Well, actually, here's a good example. When you guys look at the elections, and I've talked about this before, and we're finally to that chapter, what do they always say at the bottom? They say Mitt Romney, 23%, Herman Cain, 22%, and then at the very bottom they say, we're not really sure about this, margin of error plus or minus 4%. Right? Have you guys ever noticed that? That's where we are now. I want to be able to tell somebody, okay, from my sample, I saw 23% of the people say they're going to vote for Romney. What does that mean about the whole population then? Is it definitely sure that 23% of the population? No, I'd have to say give or take 4% for the whole population. And of course, what's going to happen if I take a larger and larger sample? What's going to happen to that uncertainty?
It's gonna
Smaller.
It's going to get small. So the bigger the sample, it should go plus or minus 3, plus or minus 2. I should be getting more and more certain about what I'm seeing. So if I take a really small sample, I might say 23%, give or take 10%, and then we're like, screw you, that's not really useful, right? Okay, so What we do in real life then is we take a sample. And of course, from that sample, we don't get mu, we get x bar. So I can't just tell somebody, okay, the actual average age of gross one is 25. I want to tell somebody it's between this and this. I'm this certain that it's between this and this. So when I go up and down, and if I want to be, for example, if I want to be 70% sure, if I want to be 70% certain, you know, that here's the average age of gross one that I found the x bar, how far up and down would I have to go to be able to tell somebody I'm 70% sure it's in between here? I have to go this many and this many standard deviations, right? Because that's what goes along with 70%. So if I catch, I often think about it like a fishing net. If I got one fish I want, and I'm sure that he's somewhere here, I can cast out a small net. But if I'm not so sure where the hell he is, I'm going to cast out a big-ass freaking net, right? So it's the same kind of idea. The more sure I want to be, the bigger my net has to be, the more stuff I have to catch. So over here, I get my sample mean, but then I go up and down this many steps. But what do we say has to happen to this? If I take a sample and I talk about the sample means, it's got to become this dude. So I desperately want you to notice, this is not a brand new formula. It's an old formula using old ideas. It's new because we haven't put them together like this before, right? So I don't know mu, I know x bar, which means I took a sample, which means this better become the new standard deviation. And it's the same stupid formula, right? That's what I'm hoping you guys see. Okay. 7.2 talks about what he did when you get percentages in here, like the Romney and the Kane thing, 22, 23%. That's not an average, that's a percentage. That's kind of got new stuff in it, though. That's why I wanted to hold off on that. So let's do this. Let's try an example out. Let's say that we find the average age of 811 gross month students. And one thing we're always assuming here, unless they're trying to make a point and they make a point with the type of horrible sampling they did, if they don't say anything about it, we're assuming it's a truly random sample. So you can't get out of certain problems by saying, well, I'm not sure this is truly random, so I'm going to go to the next one. You know, you're assuming it's truly random. Average age of 811 gross month students is 24.12, and sigma is known to be 6.091. Okay. So let me stop right there for a second. In order to use this formula, obviously I have to know sigma, right? That's the part that's not totally real life yet, but we got to start somewhere before we get freaky. In real life, I'm going to find x bar and I'm going to find not sigma. I take a sample, I find x bar, and I find s. And then in that case, something has to happen. Because am I sure about that standard deviation I found from the sample? Am I sure that that's the real standard deviation for everybody? No. So I've got to kind of cover myself for that fact. That's going to be section 7.4. But for right now, every problem in 7.3 has got to give you the population standard deviation. Otherwise, you couldn't use that formula there. Okay, and that's the part that I will say is not true to life yet, but we got to take baby steps towards real life, because real life is messy. So what am I leaving out here? Do we know everything? The one thing I'm leaving out, yeah, how to find the z-score. So I have to know how confident I want to be. I want to know what percentage I want to catch, right? So the way they're going to tell you that is they're going to say, use a level of confidence of, let's say, 90%. Or use a 90% confidence level. Okay. Now, just to introduce some symbols you're going to see here. I think this has come up before earlier, the little fish symbol. Remember that? That's actually the Greek letter alpha. This little dude is the area and the tail or tails. So what would it be in this case? If I want to be 90% confident, I'm going to catch 90% of my data. I'm going to go out far enough to catch 90%, because then I'm 90% confident that I caught the real thing. So the whole thing here is we found an average age. It's not going to be the real average age. If I go up and down far enough and catch 90% of all the ages, I'm 90% sure that I caught the real average age. That's the whole idea. So what is alpha in this case then? If I go up and down and catch 90%, so it's going to look like this? Exactly. Catch 90%, then how much is in the tails?
5.
Not each one, but together.
5,
10. Okay. How are we doing? Now, those of you who said 5%, of course, you're going the next logical step. 5% would be the amount that's in a single tail. And wouldn't that be alpha over 2? How are we doing there? Is that, I mean, don't you just cut it in half? Just like we did to get to 15 earlier. If there's 70% in there, how much is outside? 30. How much is on one side? Cut it in half. So if alpha is the amount totally outside, how do you get the amount in just one tail? Cut that bad boy in half, right? The reason I'm doing that is because the book, this is another place I don't like about the book writes this formula like this. Do you see the part that's confusing if I don't talk about it directly, which sometimes I forget to. I forget the book does this. This little piece, people think they have to throw stuff in there, right? All this is one symbol. This is the z-score that goes with this. That's all that means. And what z-score, can you look it up? What z-score would be here for 0.05 there? What z-score would have 5% below it? It's one of the asterisk dudes, right? Asterisk, it's not useful. Negative 1645, so what's up here?
1.645.
And of course, notice in the formula, it's already got plus or minus. Don't put a negative in there. It's already built in. Just put the 1.645 in there, right? So in this case, z alpha over 2 is 1.645. Don't think that there's three things going. No, there's just one thing. It's just the z-score that goes with this confidence level. That's really what it is. So what would I plug into this formula then? What's x bar?
24.12.
Yeah, 24.12, right? That's the average you found. Give or take this many, 1.645 steps, which will now be this here. 6.091 divided by square root of 811. I love it. So it takes a while to explain it, but this formula is like the most plug-in chuggable formula yet. You just plug, 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 and then chug. So the first thing we find is this piece. This piece we call the error, because that's how much we think we're off by. Here's what we found from our sample. I'm pretty sure the sample's wrong. I put money on this not being the real mean, because you just got it from a sample, right? So this is how much we're saying, give or take this much. This is how much we're saying we're off by. Is that cool? And you notice if that 811, if I made it bigger, wouldn't this become smaller? So then it would get tighter. I think I'm off by less. That only makes sense. The bigger the sample, the less I should think I'm off by, right? Okay. So what is this error piece then? Wait, no, Jeff. Just get over here. Can't write that way. Oh, shit. That's why I need to get a cameraman.
0.525.
Yeah, so when you plug this in the calculator,
24.33.
oh wow, I'm getting like several different things.
24.33.
I think I have to go out my own calculator. What you got for me?
Yeah.
Thank you.
2213.
Oh, I see. Don't add it to this yet, because you got to do the 1.645.
I did.
Okay, okay.
First I did
Point
6.091
091
plus square root of 11.
divided by square root of 811. Yeah, so I get 0.352, roughly, right? 3518, whatever.
How'd you get that?
3518.
Because what's the error? The error is 1.645 times 6.091 divided by square root of 811, right?
Okay.
Let me put it over here for you guys. The mean was 24.12, give or take. The z-score for 90% confident was 1.645. Standard deviation was 6.091, but now I need it for 811 people at a time. So I got to change that standard deviation. Yeah.
So were we trying to find? Were we trying to find those questions?
0.352.
Yeah, is it asking for the error, or what's it, what are you asking for?
All right. To do this whole problem, don't I first have to know what I'm going to add and subtract? All right, so that's what we just did. We figured out what the hell I'm going to add and subtract, and then you add and subtract it. So the last step now is to take this plus this and this minus that.
But is that what you're asking for, is what those numbers
So I
are?
want to know, just like we did in the other example to get us into this section, I want to know between what two ages, in this case, would the real age be? All right? So when you take this minus this, and look at the error is pretty damn small, right? Why is the error so small? Because we're allowing to be 10% off, aren't we? We're saying I'm only 90% confident. So it's pretty small confidence, and we got a pretty damn big sample, 811. So I shouldn't really be off by that much. So what's 24.12 minus that?
23.77.
23.77? And what's 24.12 plus that?
24.47.
Yeah, 24.47, rounding up. I like it. We're rounding it off. All right. So for those of you who don't like the math of this, here's something even better. There will be an English part at the end. Yay! Chapter 7 and Chapter 8, you will be required to write a sentence explaining what the hell you just did. And here's what this would look like. Let me put this over here for you guys. Really, one really bad thing about this room. 23.47. 77 and 24.47. 4.47. Definitely. So it would be kind of weird to say, what were the age of the people that came? Well, they were between 70 and 20. No, you'd say.
I was trying to put it in the order of, plus negative.
Ah, I got you.
That's
So it's
what I
always
was like,
smallest to
maybe.
biggest. Yeah. So here's what you need to write at the end of this. Here's your statement that you can write. We are 90% confident that the interval 23.77 to 24.47 will contain the true mean age of Grossmont students. So in Chapter 7, that's the kind of thing I need to see at the end of a problem. In Chapter 8, we're going to have a similar kind of thing that we have to write at the end of those problems. Okay.
So on your original question where it said find the average age, we're going to have a range. Is that what you're saying? For our
Exactly.
answer?
It's the best we can do, right? The absolute best I can do directly is to find an average of a sample. To make it better, I say, well, then I think it's between this and this. And I'm 90% confident about that, right? So what's the chances that it's not between this and this? 10% chance that it's not in there, right? So what would you do if you wanted to really capture it better? If you only wanted there to be a 1% chance you were wrong, what would you change?
Bigger sample.
well, you could make a bigger sample, but let's say you can't pick anybody else, and you want there to be only a 1% chance that you're wrong, you would change this 90 to 99. And you look at that z-score, and that z-score would be bigger, wouldn't it? Because it has to be further out. That's bigger, makes your error bigger. Do you see what I'm saying? So if you want to be more sure that you catch a certain fish, don't you throw out a bigger freaking net? So in that case, same idea. To catch the real mean, and I want to be more sure, I make my interval a little bigger. Then I'm more sure that I caught the real mean. So what I've got going on here is there's a real mean somewhere. Here it is. And I take a sample. And then I say, okay, the real mean is somewhere in here to here. And in this case, it was, right? So we create this. This would be like the 23.77 to 24.47. And I'm saying there's a 90% chance, I'm 90% confident that this interval catches that guy. So what's the chances he's outside? Of course, like we said earlier, there's a 10% chance that he's outside. That's a pretty high chance he's outside, to tell you honestly. Would it be unusual for him to be outside? No, that's not good. So instead, I could make a 99% confidence interval. And there's only a 1% chance he's outside, but now I'm telling somebody this bigger interval, right? So I'm being more honest, which makes me look like I know less, but it's being more honest. So you got to give them some room. All right, let's do another problem, because these are just kind of take practice looking at what they look like and then writing the statement. Yeah.
I don't understand the error part. The 0.352.
So this is the sample average we found.
Right.
If I want to be 90% sure that the interval I make from something below this to something above this, if I want to be 90% sure that that catches the real mean, because this should be close to the real mean, right? Say 811 freaking students. If I truly took a random sample, that should be close. That's why it turns out my error didn't have to be that big. If I just take 24.12 and I go up and down by this much, I am 90% sure that I caught the real average. You guys kind of with me here? What could have happened? Even if I take a random sample, could it have all been younger people? There's a chance, right? That's why there's still a 10% chance that I'm wrong. That it actually is less or more. And that's why some people hate stats. They're like, why don't you give me a real answer? Because freaking stats is real life. Real life, you don't get totally straight answers, do you? You get, well, this might happen or this might happen. That's why I love stats. It's the most honest math there is. It says, shit, I don't know. But at least it makes sense. If I get a bigger sample, my error goes down. If I want to be more sure this number goes up, my error goes up. So I catch more stuff to be more sure, right? It shows you the interplay of what you want and what's that got to happen. Okay. Let's try another one.
You have to remember number from 90%, 95% targeting, right? Like the label.
Well, I'll still let you use the z-score chart.
Yeah, but we have to remember that if 90, we're gonna get 0.05, right? And
Oh, shit.
gonna be 1.645. If 95 is gonna be 1.96.
You don't have to memorize those, no. I'm going to let you use the z-score chart. And you've already found the little baby chart, it sounds like. There's a little baby chart in your z-score chart that speaks directly to these. So if you look at the confidence level of 0.90, what's right next to it? 1.645. What if your evil teacher asks you to make a 97% confidence interval, which he will do, because he's evil, as I already said. Then you'll have to know how to get your own z-score. You can't just use the little baby chart to get it.
What baby chart are you talking about?
So if you look at your z-score chart, where did it go? Oh, you have it going. On the positive z-scores, right down here, there's a little common critical values. Confidence level, critical value. This one with a confidence level that was up here was 90%, right? So if you look at 0.90, 1.645. These are the ones that are most often used. In fact, 95 is the most often used one. But that doesn't mean they're the only ones that you use. So you got to know how to find it the old-fashioned way, not just the little baby chart method. Okay. So let's try one more problem, and then we'll head out. Let's say sample of And this is the cheap stuff here, right? I definitely don't have a high performance car, so I think right now it'd be like 380 something, or
Sure.
right? I only go to Arco nowadays, so it's say 387.
I'll go to 369.
Sigma is known to be let's say 19 cents. Sure. Because I love those crazy people up in Carmel Valley paying $4.50 for gas right now. It's like, what the hell? Blah, 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 blah. So I want to find the 99% confidence interval, which from here on I will write as CI because I don't like writing that much. So CI will mean confidence interval. Okay. So now that we've gone through the torture of Jeff explaining the concept, you can take the formula. We know we got to use this formula here because it's a confidence interval for a mean. If it was a confidence interval for a percentage, I'd use the one that had a p in it for percentage. Right. So the first step is, what situation am I in? Now I say, what do I know up there already and what do I not know up there already? I know every damn thing in there except, of course, for what?
The error.
Z. I know X bar, I know sigma, I know N. I have to be given these things, right? And in fact, just so you know, they will start giving you lists of data again, which you will put in the list one and then use one variable stats to get what you need. You with me? Sometimes they'll just give you raw data. They're not going to tell you X bar in sigma. You have to calculate it. So you just do it in your lists, one var stats. So how do I get that z-score that I need for a 99% confidence interval?
2.575.
Beautiful. You can look up in the little baby chart. How would I do it the old-fashioned way?
You look on versus
Yeah, how much is outside? What's alpha?
0.01.
0.01. So what's on one side?
0.005.
0.005. Cool. If you look up 0.005, it will be an asterisk, which would follow down, and you would see exactly what the little baby chart says.
10001.
Careful.
Negative 0.2575.
That's not a z-score, right? So
2.575.
yeah, 2.575, right?
Yes.
So my z-score that I want to use in the formula is 2575. The plus or minus is built in. So what would I put in there? Let me go over here so everybody can see a little better. Yeah, so it's X bar plus or minus Z sigma over square root of N. So X bar is 387. Give or take the Z score we just found
2.575.
times the standard deviation.
0.19.
Good. Divided by the square root of the sample size.
71.
71. I like it. And my errors can be like 0.07 something, 0.075 something. 0.0. Okay, cool.
2.5.
Sounds about like what I was expecting. Is that what you guys are getting
yeah.
for the error? Okay, and then you got 3.87 minus that, and 3.87 plus that. In general, you can round to the same number of decimal places there, right? You don't have to have that 1 at the end, really. You don't need that 8 there, then, do you? But, oh well, we'll just keep going. What do you guys get for that? 387 minus 058? 3.812. 2. And then this will be 3.928. Yeah. So from $3.81 up to $3.93 almost, right? So how would you word that statement?
We're 99% confident.
We are the 99%. I mean, we are 99% confident that the interval,
$3.
3.81.
yeah, 381 to 3928 or 393. It's money, so you can round it up to money to a couple places.
Will contain.
Good. Will contain.
Did you say the average or just the price of gas?
We're trying to find the true
The true average.
Average.
Or the true price.
the true average.
Okay.
To say the true price, you can't say that because every single gas station has a different price, so I can just find an average price. We're 99% confident that the interval this to this will contain the true average gas price. And that would be for all gas stations, right? So of course, if my sample sucked, all my analysis is going to suck. So this is always assuming that I picked those 71 gas stations randomly to have this come out to something I can trust.
In the first question, we asked for average age, but we stated a true mean age, and this one we put true average.
Oh, I don't know.
Either or.
Average and mean are the same thing. They mean the same thing. Yep.
Go ahead.
Yeah, it should be negative 0.39. Oh, you just were, okay. You just looked, your eyes just wandered up here. You got it. This should be 3.9. Yeah. That's why I only took 1. Oh, it's up here. So my eyes, normally for math, I look at the bottom. Circle that bad boy so I know. Okay. So circle that at the end so I know where to look.
I know, right?
Exactly. Because I'm looking at this one,
Yeah.
and I cannot.
2575. Okay. So if I want to be 99% sure, that means there's 1% on the outside, which means there's 0.005, right? Half a percent. 0.005. The closest I can get to it is here. Follow the asterisk down. 2575. Because they're taking the average between 2.57 and 2.58. Cool. Of course, the shortcut is here's your 99%, 99 confidence level, and there's the z-squared goes with it.
I still my quiz today because I was off today.
You can do the, yeah. This is what you need to average on the whatever quizzes and the next test and the final. You have to average this to pass the course with the way things are now. But of course, you can make corrections on this, and that will pick your grade up a decent amount if you get enough of them right. But if you leave it the way it is, this is what you have to average, and you know how much homework you turned in. That's what you have to average to pass. So you can make that better by doing corrections. Yeah. Cool. Is this from Oh, okay. And are you sure that? Oh, okay, I'm with you. This is after you figured out the way to do it. Then you have to do this is x. This is p of x. X p of x to get the average. X squared p of x. Towards the formula, right? The whole thing from chapter 5. Yeah. So you have to do the x p of x, and you got those. Now x p of x. X squared p of x. And then you got your. Throw what you get to add those up, put it in here.
Okay.
You have to do that.
It's
Whole
just
thing. Yep.
right there. Percentage of students that it shows number 3 is 9.4%.
Okay.
It's just
Oh,
right
right
there in the
there.
chart. Yeah,
Yeah,
you just look at the chart.
She
And
did
that's
this
what it
one
is.
before. 280.
Made that one too complicated.
Okay. Part A is a little weird because to find the expected number, I have to know the probability. And so I'm really asking what's the probability that a quarter will be rejected. It'll be rejected if it's outside of this range, right? So then you make those two in the z-scores. Look up those z-scores and get the right area. So in this case, this is a little weird because you want the areas that are out here. So you look at that z-score, it's going to be exactly what it is. Look up that z-score, you got to do 1 minus to get that. And then you take 280, you want to do NP times the probability that you get. That's your expected value of the n times p.
Okay.
Yep. Cool. I think the other ones are a little more, the wording is a little bit more like what we're used to.
Okay.
Cool.
I have a question about, you said there was, for the next math class I would take, there's 2 classes that you can combine into one. I think it was
Oh, with the
176.
free calculus?
Yeah. Is
So you
it
can take
170?
170, 175, and that would be a total of 7 units. Or you can take 176, which is 6 units, and that does both 170, 175 in one semester.
So 176 covers 170 and 175?
Yes.
Okay.
And it all depends on what else you're doing, and because that's a
Hard one.
yeah. And you probably want to get the one that meets not 2 days a week, because that sucks to be in because you'll be in the class 3 hours each day. Then you want 3 or 4 days a week would be better. Yeah.
Okay.
Yeah.
All right, thanks.
Sure.
This is what I wanted to ask about. I'm so sorry.
It's okay.
But this, like, I mean, this looks, well, I gotta come to your office and talk to you, but for my homework, right here, I've turned in everything to you. That's what I was asking you last week about,
Right.
except for 6.6.
Let me write this down.
Then you have all of the 3s, 3, 2, 3, 3, 3, 4, 5s. 5, 2, I turned in all these to you when I came. The 3s I gave you from the beginning.
No
I
problem.
corrected them.
Like I said, it's not no evil intent for me missing those. It's a classic human error. So I'll just go back and see if I can find those. Yeah. No problem.
I'll come in and talk to you tomorrow.
All right.
Tate wanted me to remind you about
Oh,
the
shit.
dinner on Thursday.
I didn't even check my email. He was going to email me.
Yeah,
of
he said
course.
he did it yesterday. Yeah.
Yeah,
But
last night because I haven't checked it this morning yet. So I'll probably send an email out because this is Thursday. So I'll email the whole class because he's at 4 spots open for the dinner, right? Okay.
yeah.
All right. Thank you.
Yep.
Yeah, actually I see here, I'm missing 2.4 homework. Yeah, 2.3.
Ah, cool.
Yeah.
2.4 is good.
Yeah.
Gotcha. Yeah. Cool. Okay.
And the last time I didn't turn in the quiz, the last quiz. So it's possible to turn it in
Yes.
today.
Cool.
Are you gonna have time in your office? Or are you gonna go somewhere?
I gotta go 11 o'clock meeting. Yeah.